G'day, welcome back. Let's continue our lessons into the types of chemical bonding, where today we're looking at sigma and pi bonds, hybridization, and molecular geometries, where our lesson objective is to understand how sigma and pi bonds form and investigate the concept of atomic orbital hybridization. Then we're going to identify molecular geometries and understand bond angles observed due to electron-pair repulsion. As always, our learning outcomes from the Cambridge curriculum that we will be looking at. So we said last week we have three types of bonding. We have our ionic, our covalent, and our metallic. Our understanding of the ionic and metallic model stay relatively unchanged. It was just a little bit of a recap. You might have seen all that before. Our covalent bonding, we recapped it, but today we're really going to advance our understanding into that because it's like when we looked at the electron and we said the electron is a lot more advanced than we've previously been taught, so we need to advance our model. Same thing with covalent bonding. We really need to advance our understanding of how these covalent bonds form and their properties. So covalent bonds, we said, is the sharing of an electron pair. That's a very simple definition. However, we know that electrons have a wave-particle duality and they exist in orbitals, so we can be more specific. Covalent bonds are more specifically the overlapping of atomic orbitals to form molecular orbitals. So you have an atomic orbital from one atom, an atomic orbital from another atom. They overlap and you form a molecular orbital, which is where they're sharing those electrons and you get a strong bond between those two atoms. We have two kinds. We have what are called sigma bonds. Sigma is coming from the Greek letter for S. S obviously being one of our atomic orbitals, the S orbital. These are our single bonds. So they aren't just made from the S orbitals, they can be made from other orbitals as well. But whenever we see a single bond, that's what we call a sigma bond. The bonds are symmetrical and in line with the nucleus. And we're going to look at what this means in a lot more depth with some models that I have in just a moment. But let's just quickly go over these two types of bonding. Pi bonds. This comes from the Greek letter for P. Pi being the Greek letter for P. Again, P orbitals is where it comes from, the S and the P. These are our double and our triple bonds. And note that we need to form one sigma bond before forming a pi bond. Bonds are non-symmetrical and not in line with the nucleus. What do I mean by all of this? Let's have a look at some examples. We're going to draw some simple examples like the ones that we looked at last time. So I have H2. So we have one covalent bond between the hydrogen like that. If you need a recap on this, go see the previous video. That tells us how we know how to draw these molecules. So this has one single bond. So this single bond is a sigma bond. This symbol here, sigma, this is the Greek sign for sigma. So this bond is in line with the nucleus or the nuclei of these two atoms. Now again, I've got some models that's going to illustrate that a bit more clearly. Let's look at carbon dioxide, CO2. This is C double bond O, double bond O. Now, in this case, we have a sigma bond. We've still got a sigma bond because you have to have a sigma bond before you form a pi bond. So we have a sigma bond between the carbon and this oxygen. We also have a sigma bond between the carbon and this oxygen. But then we have a double bond, and these are what are called our pi bonds. So in this case, we have a pi bond there and a pi bond there. This being the Greek symbol for pi. I'm sure you would have seen that in maths a lot. So in our carbon dioxide molecule, we have two sigma bonds and two pi bonds. Let's look at a third example. Let me get my eraser so I can make some room. Cyanide, HCN, looks like this, HCN, HCN. Now in this case, we have a triple bond present. So if we were to label the pi and sigma bonds, the single bonds are the sigma bond, so we have a sigma bond there. We also have a sigma bond between the carbon and the nitrogen over here because we said that you need to form one sigma bond before forming pi bonds. We're going to go into why that is in just a moment. But that means we have one sigma bond between the carbon and the nitrogen here. However, our double and our triple bond are these pi bonds. So in this case, we've got two sigma bonds and we've got two pi bonds as well. So sigma are single bonds, pi are our double and triple bonds. Let's delve into this in more detail. Sigma bonds. A single covalent bond is a sigma bond. Forms from the overlap of two atomic orbitals to form a molecular orbital. The amount of overlap determines the strength. Let's consider why that is. What is holding the electrons and holding these two atoms together is that nucleus, the positive and negative electrostatic attraction that is present in the atoms. So if you have more overlap between the orbitals, it means the electrons are going to be closer to the positively charged nucleus of each atom. Now we said the closer that the the closer that the electrons are to the nucleus, the closer the negative is to the positive, the more stabilized, the stronger they are going to be held. Similar to how we're looking at how the electrons are held in just the atomic model. So let's look at an example in more depth. Sigma and a pi bond between two s orbitals. For example, hydrogen. Let me just draw a hydrogen again. Hydrogen subshell electronic configuration. We have a simple 1H. It's going to have 1s1. So if I draw a hydrogen with one lonely electron, if we have hydrogen gas, which I drew before, H2, like that, we said that we have one sigma bond present. So what we get is an overlapping of two orbitals of two hydrogen atoms to form a covalent bond, a shared pair of electrons. So we know this hydrogen has 1s1 electron, this hydrogen has 1s1 electron as well. So I've got a whole bunch of models with my favorite thing, balloons. Now I'm going to start with a very simple one, which is just s orbital, s orbital. Now we talked about the s orbital being spherical in a previous video, so you can go look at a discussion on that if you need a refresher. But if we have one s orbital, these two atomic orbitals overlap and we form a molecular orbital. We've got a nucleus in the center of each of these two hydrogen atoms that is now binding this shared pair of electrons to both of them. So if we look at a diagram over here, we get an s atomic orbital overlapping with another s atomic orbital to form the molecular orbital that is now a slightly different shape. However, the sigma bonds, even though they're called sigma bonds after the Greek letter for S, they can form between other types of orbitals as well. P orbitals can also overlap to form sigma bonds. When they overlap, they are modified. One lobe becomes bigger, includes some character of the s orbital, and this is this idea of hybridization. They become hybridized. We're going to look at what that means in the next slide. For now, we're just going to look at an example of a p orbital overlapping with an s orbital. So if we think back to a few videos ago, we had our p orbitals. Remember, the p subshell can hold 6 electrons, so we can have 3 orbitals. Each orbital holds 2 electrons. So we have the py orbital, which is my yellow balloons, that can hold 2 electrons. Px, which are the pink balloons here, and then pz, which are the green balloons. So let's show a p orbital overlapping with an s orbital, for example, in a CH bond. What happens is they become slightly modified. One lobe of the p orbital becomes bigger than the other orbital and starts to sort of incorporate some of this s orbital that is beneath it. So we have a modified p orbital overlapping with an s orbital to form a sigma bond, for example, in a CH4. If we got CH4, like that. This is a sigma bond. This is a sigma bond between one of the p orbitals of the carbon with the s orbital of the hydrogen to form a covalent bond. If we look at that on the slides, we said that the p orbital becomes modified where one lobe becomes slightly bigger. So you get the overlap of the p orbital with the s orbital to form a molecular orbital there, which is a sigma bond, a covalent bond. We could also get 2 p orbitals overlapping. For example, in a carbon-carbon bond. So if instead of methane, let's say that we had ethane. Where have I put my marker? There it is. So in the case of ethane here, we have a sigma bond here. This is still a sigma bond. However, it's the overlap between two p orbitals instead of a p and an s orbital. So we've got one p orbital from the carbon there, one p orbital from the carbon there. These orbitals overlap and you form a molecular orbital. If we look at a diagram of that, it looks like this, where the p orbitals become slightly modified, one lobe becomes bigger, and then you form a molecular orbital like so. But we said that the p orbitals have changed, they've hybridized. They're not really p orbitals anymore, they're slightly modified. And that's this idea of hybridization. The mixing of atomic orbitals to have some of the character of each of the orbitals mixed. Now there's a few ways that things can hybridize, and they're always hybridizing for the same reason that chemistry does anything, to exist in low energy conformations. Things don't want to have energy if they don't have to have energy. The hybridization is the same, it's just a way to reduce its energy levels. So we're going to look at sp3 hybridization, sp2 hybridization, and sp hybridization. The first of which is sp3 hybridization, which you might guess has something to do with these s and our 3p orbitals, and you'd be correct. In sp3 hybrids, the one s orbital has mixed with the 3p orbitals to create 4 sp3 orbitals. These orbitals have a quarter of the s character and 3/4 of the p character. So they're no longer s orbitals, they're no longer p orbitals, they're now sp3 orbitals. Let's think about this. If we have a carbon atom which has 6 electrons and we do the electronic configuration 1s2, 2s2, 2p2, 2, 4, 6 electrons for our carbon. If I was to draw this in a sort of energy diagram, we have our 1s2 electrons down the bottom, then we would have our 2s electrons and our 2p electrons. So if we do it like this in the sort of the unhybridized low energy state, we would have an electron there. We then had a rule that said we would fill this energy level before that energy level, so a second electron would go there. We then fill this one. We've got one more electron. We fill in the vacant orbitals before pairing up. So we might have something like that, but if we draw a carbon, we say we got 4 electrons in the valence shell that make 4 bonds. So in the case of something like CH4, we have a covalent bond there, a covalent bond there, a covalent bond there, and a covalent bond there. So that means that we need to have 4 electrons that can make a pair. So we've discussed the idea that electrons can move and jump between energy levels. So we have the unexcited, unhybridized carbon, but we could also excite one of these electrons up here so that now we can make a covalent bond there, covalent bond there, covalent bond there, and a covalent bond there. However, the problem here is that I've told you these are sigma bonds, and all of these bonds are equivalent. This is a sigma bond, this is a sigma bond, these are all sigma bonds. However, if we were to make bonds with this sort of conformation, well, this electron pair here would be in a lower energy than this one here, and that wouldn't be reflected like this. So what actually happens is we have a hybridization that occurs where I have, this is my valence electrons in a carbon atom in the excited state. What they do is they hybridize. Instead of having 1s and 3p orbitals, they hybridize into 4 sp3 orbitals. These orbitals are all of the same energy levels, and these are what make our 4 sigma bonds that are all equivalent. Let us show this with a model. So if we have 4 sp3, if we have 4 sp3 orbitals that are all equivalent energy levels and all have electron density within them, the furthest apart 4 electrons can be is in a tetrahedral shape. So I got 4 things that are tied by the nucleus in the center. These are negative charges. These negative charges repel each other. The furthest away these 4 regions of electron negative chargedness can be while still being tied by the positive nucleus in the center is in this tetrahedral shape, and this is an sp3 hybridization. Gives a tetrahedral arrangement around the nucleus. However, this can't form double or triple bonds. So what can happen is we can get a sp3 orbital to overlap with another sp3 orbital like this. So this might be in the case of two carbons. If I've got a carbon bond like the example I showed you before, I showed you with p orbitals, whereas really this would be sp3 orbitals. So this is a sigma bond of one of the sp3 orbitals overlapping with one of the sp3 orbitals to form a covalent bond between these two. However, this can't form a double or triple bond because it's just too much energy for another of the two s orbitals to overlap like that. Everything's just too close together. All these electrons are no longer happy. This is too high energy because all these electron clouds, I don't have enough hands, all these electron clouds are repulsing each other. So we can very happily form a sigma bond, but if we want to form a double or a triple bond, what has to happen is we have to have a different kind of hybridization that will allow that to occur. So this is where we get our formation of our pi bonds. We need to hybridize differently in order to form a double bond. So we still have one sigma bond, but now we have one pi bond. In sp2 hybrids, the one s orbital has mixed with the two p orbitals to create three sp2 orbitals. However, we've left one unhybridized p orbital that can form a pi bond in addition to the sigma bonds. What do I mean by this? I'll come back to that last point in a moment. So this is our excited state of our unhybridized carbon. In sp2 hybridization, we mix an s and two of the p orbitals, but we leave one of the p orbitals unhybridized, and this is then free to make a pi bond. So in this case, we form an sp2, which isn't an s orbital, it isn't a p orbital, it isn't an sp3 orbital, it is an sp2 orbital. However, we've left one of our p orbitals unhybridized. This means that a double bond can then be formed by the overlap of two unhybridized p orbitals. Let's look at an example. So this is my sp3 hybridization, where we mix the s and the three p's to get four equivalent sp3 hybrid orbitals. In sp2, we leave one of the p orbitals unhybridized. So this yellow one is representing my unhybridized p orbital. So this is that p orbital there, and then I get three equivalent sp2 orbitals, which are my silver ones. So what we can do here is we can form a pi bond. We can form a double bond. For example, in the case of C, double bond C. So now we've got a sigma, and we've also got a pi bond. So I've got a sigma there, I've got a pi there. We can have our sp2 orbital overlap with our sp2 orbital to form a sigma bond. So that would be the one sigma bond we form. Now we can talk about why it's called the sigma bond. And we talked about the idea that it's in line with the nucleus. So we have a nucleus on that atom in there, we have a nucleus on that atom in the center in there. The sigma bond here is in line with the nucleus, and that's why it's called a sigma bond. But we have our unhybridized p orbital over here, our unhybridized p orbital over here. Unlike our sp3 hybridization, which couldn't form that double bond because the electrons are just too close to each other, these unhybridized p orbitals are in great geometries to overlap with each other. If I use my hands all like this, I don't know if we can see this, and form one pi bond. So remember that one p orbital has two lobes, so we get the two lobes to overlap in the two unhybridized p orbitals, and we form the pi bond. Now the pi bond, as in the two yellow balloons, is not in line with the nucleus. It's above the nucleus and below the nucleus. So that's why it's called a pi bond. Sigma bonds between my gray balloons are in line. Pi bonds with my yellow balloons are not in line. So we draw that very simply over here with our second bond being our pi bond. Rightio, so we can form a double bond with sp2 hybridization because this unhybridized p orbital can overlap with another unhybridized p orbital because all the electron clouds sort of line up with each other. If we want to form a triple bond, we got to hybridize differently again. Now this might be a good time to pause and see if you can figure out what's going to happen in the next step. What kind of hybridization what would this diagram look like for that? So if you want to pause and have a go at that now, I'm going to resume right now. We had sp3 hybridization, sp2 hybridization. You might have guessed we're going to have sp hybridization. Same concept as the previous one. We need to hybridize slightly differently. In this one, we have one s orbital mixing with just one p orbital to create two sp orbitals. And that leaves two of our unhybridized p orbitals that can now form two pi bonds. Therefore, a triple bond can form. So you form in one sigma bond, two pi bonds, a triple bond. One unhybridized p orbital overlaps with another unhybridized p orbital. Let's have a look. The other unhybridized p orbital can then do the same. So this is the diagram we've seen a few times now. If we sp hybridize, we mix the s with one of the p to get two sp hybrids, like that, and we leave two unhybridized p orbitals staying the same as they were before. So this would be in the case where we've got a C triple bond C. Now we've got one sigma and we've got two pi. This would look like this for sp hybridization. There we go. We have a hybridized sp orbital. We've got two hybridized sp orbitals. Then we've got one unhybridized p orbital, so we could say this is the px. We have another unhybridized p orbital, so we could say this is the, this would be the py, this could be the px. So we've got two unhybridized p orbitals, which are the one there, so one of the red balloons, and then another one of the red balloons there. And then we have our two sp hybrids, which are the gray balloons. So let's show how this could form a triple bond. All right, let's see how many hands I've got. We can form the sigma bond, because remember, in the triple bond, we always form a sigma bond first. And we can see this because our sp hybrids are going to overlap and form a sigma bond. It's called such because it's all in line with the nucleus. The nucleus is in there, the nucleus is in there, our sigma bond is in line. Now, hopefully what you can see here is that our p orbitals, our unhybridized p orbitals, are in line to be able to overlap. Now, I don't know if we're gonna have enough hands here. Let me grab the other model. So we got unhybridized p orbitals that can overlap like so. So we have in the center between our two gray balloons is our two sp orbitals overlapping to form a sigma bond, called so because it is in line with the nucleuses. We then have a pi bond forming between the overlap of two unhybridized p orbitals there. We then have a second pi bond forming between the overlap of two other unhybridized p orbital to get a triple bond, one sigma and two pi bonds. So hopefully this helps to illustrate the orientation and why we have to have this hybridization in order to get these double and triple bonds, because it just means that these electron clouds can line up with each other, the orbitals can merge, and you can form molecular orbitals like so. So to summarize all that, big summary, let's look. We have our unhybridized carbon in the excited state. We have our sp3 hybridization, where the s and the 3 p's all hybridize to form this shape, like that. We've got 4 equivalent orbitals, make a tetrahedral arrangement. So this is it's a mixture of the s and the p, so it's going to have slightly less energy than the p because it's incorporating this s, so it's going to be like that. We then have our sp2 hybridization, where we have one of the s and 2 of the p's hybridize and leave one unhybridized p orbital, which will give us this type of arrangement where we've got 1, 2, 3 sp2 orbitals and then one unhybridized p orbital that remains. Now we can see the sp2 is slightly lower energy than the sp3, and that makes sense because it's got less p bringing it up, so it's going to be brought down more by that s. And then finally we have the sp hybrid, which is this case where we have 2 hybridized sp orbitals and then an unhybridized p orbital, yellow one, and another unhybridized p orbital, the purple one. We can see that this is going to be even less energy than the sp2 again, but not as low energy as the s because it still has some of the p, but less of the p than the sp2 does. Okay. Hybridization will affect the shapes of molecules. Methane has sp3 hybridization, so it'll be tetrahedral. And that's this balloon model, the blue one that I keep showing you, sp3 tetrahedral. So we can rationalize why something like methane will have this geometry, and it's because of the hybridization that it has. It's because of the hybridization that it has. Whereas ethene will be sp2 hybridization, which will be trigonal planar, which is due to that model that I showed you previously. That concludes the first part of our lesson. Let's look at molecular geometries in a bit more depth. Now, we looked at them last lesson a little bit, but we're really going to dive into these shapes and the bond angles in these shapes. So, if we have methane, CH4, and if I draw that on a whiteboard, I draw it like that, because this is the farthest things can get away from each other in two-dimensional space. If you've got 360 degrees and you want these four things to be far away from each other, you're going to put them at 90 degrees each, because that's the furthest way. But we just saw that in 3 dimensions, that is not the case. So this isn't the correct way to show it, because our model is limited by its two-dimensionalness. Anyway, new word there. Because our model is limited. Whereas we've got to find a way that we can show this tetrahedral geometry in a two-dimensional plane for when we write it down in our books. And that's what we do with these dashes and wedges. So we have these pictures where the dashes are going into the plane of the board, the wedges are coming out of the plane of the board, and the lines are just in plane with the board. So if I draw that over here, I go carbon, H, H, I have one dash, I have one wedge. And what this is showing, it's showing that this hydrogen is going back, whereas this hydrogen is coming out. And I can model that against this one here by saying, well, these two hydrogens are these two hydrogens, these are on the same plane. This hydrogen is this hydrogen here, where it's coming out, and then this hydrogen is the hydrogen back there, which is going into the board. So the same way that you sort of do perspective diagrams for a cube, you know, where you've got I haven't drawn a cube in a long time. Let me try that again. If you've got a cube like that, where you're showing, you're representing a sort of three-dimensional shadow in 2 dimensions, this is doing the same. You're representing a three-dimensional shadow on 2 dimensions. So let's have a look at some examples with different hybridization. We have C2H6, C2H4, and C2H2. How will we draw these? Let's just draw these normally in 2 dimensions first. If I have C2H6, I'm going to have 1 carbon like that. I'm going to have 3 hydrogens like that. I'm going to have 3 more hydrogens like that. However, this wouldn't be looking like that. It would be looking like this, because we have 2 sp3 hybrids. So we've got to show one of the hydrogens going back and coming out here, and the same thing over here, one of the hydrogens coming out and going back. So if you wanted to show this in 3 dimensions, we need to write this showing that tetrahedral geometry. So we can have 1 hydrogen going out of the board, 1 hydrogen going back into the board, 1 hydrogen on the plane, this bond on the plane, and then the same thing over here. Now it doesn't matter where you put the dashes and where you put the wedges, as long as you've got 1 dash and 1 wedge on each of the carbon atoms, because each of the carbon atoms has tetrahedral geometry. What about in the case of C2H4? C2H4. Now this time we have a double bond. H1, 2, 3, 4. If we have 1 double bond, we have sp2 hybridization. So that's this model here. Now, when I line these up, and when I have my double bonds coming over like that, I don't have enough hands, but if we just look at the silver balloons, what we see is that all these silver balloons are on the same plane as one another. If I look down like that, they're all on the same plane. So this is a trigonal planar geometry. Now, because these are all on the same plane, I don't have to show any going in or going out of the board, because if I do a simplified model without the p orbital there, we just have this. And this is the furthest three things, which is the same. There's nothing going in or going out of the board there. So it's just going to be the same as this. So in this case, we don't need any dashes or wedges because all of these bonds are going to be on the same plane. Similarly to when I have C2H2. So this is where we have C triple bond C with a hydrogen like that. This is the case of our SP hybridization, which if I get my SP model back, give me 1 second to get all my hands over everything. If we just look at the gray balloons, all of these are on the same line. So this is just going to be a linear geometry. This is just going to be a straight line. Our gray balloons, nothing going into, nothing going out of the board. It's just going to be drawn the same way as that one there, like so. These are all the shapes we looked at last time that we need to be familiar with. Let's look into them. Let's start at the top with something like linear. Linear, as in the case of the one we just looked at down here with the C2H2, might also see it in the case of something like carbon dioxide. Carbon dioxide, C double bond O, double bond O. We have no lone pairs on the carbon here, so we've just got two regions of negative space. The furthest they can be away from each other, 180 degrees. If I have a carbon nucleus there, oxygen nucleus there and there, this is going to be 180 degrees. So again, we can just show that we don't need any dashes or wedges because they're on the same plane. If you look at it down there, you don't see anything sticking out. They're on the same plane. Let's look at these ones here. We're going to come back to our trigonal planar, trigonal bipyramidal, and octahedral in a moment. Let's look at these ones where we've got four things bonded or four things around it with varying numbers of bonds or non-bonds. Not all electron pairs repel each other equally. So all three of these are based around this shape, where in the tetrahedral we have 1, 2, 3, 4 things bonded. In the trigonal pyramidal we've only got 1, 2, 3 things bonded, and we're left with a region of lone electron pairs. And in the nonlinear we've got 2 things bonded, and we have 2 regions of 2 pairs of non-bonding pairs. Alright, but not all our electron pairs repel each other equally. Bonding pairs are being shared between 2 nuclei, whereas non-bonding or the lone pairs only belong to 1 nuclei. So in the case of a bond here, this electron pair is being shared between both this and that atom, whereas on this one, this non-bonding pair, this lone pair, isn't being shared with anything else except for that one atom. So this means that the non-bonding pairs have a larger cloud, electron cloud, and they're closer to the nucleus, so they will repel each other more than bonding pairs will. And here's the order of electron pair repulsion. Lone pairs will repulse the most with other lone pairs because they have the biggest cloud and they are closest to the nucleus. Lone pairs will then repel bonding pairs in the next strongest order of repulsion, and then bonding pairs will repel bonding pairs with the weakest order of repulsion. This will affect the bond angles seen in these 3 shapes. Let's draw some examples. Let's start with the tetrahedral that we've talked a lot about today. And we're going to stick with our old mate CH4. So I'm going to draw CH4 again. Carbon, H there, 1 going back, 1 coming out. Now, we have 4 non-bonding pairs. Sorry, no, we have 4 bonding pairs rather. And all of these are exactly the same. All of these are equivalent, so they're going to be repelling at each other the same amount because they're all bonding pairs between the same atoms. So what we see is that we get an angle, a bonding angle of 109 degrees, and you need to know these numbers. So a tetrahedral shape will have bond angle of 109 degrees. If we have one of these left as a lone pair, we get a trigonal pyramidal, such as in NH3. So in this case, we've got nitrogen can make 3 bonds, so we have a H there, well, that's a big wedge, H there, but we have a non-bonding electron pair. Now this still has negative charge. This is still going to want these away from it, and in fact it's going to want these away from it even more because these electrons are closer to the nucleus and they have a bigger electron cloud. So I can draw a sort of a bit of a cloud like that. So what we see here is we get a bond angle in there of 107 degrees. So we have a smaller bond angle because the lone electron pair, let's say this one here, is pushing these other bonding pairs away from it even more, so they're even closer together. And this is our trigonal pyramidal. So it kind of makes a pyramid. And the last is the nonlinear or V-shaped or bent or angular. It goes by a lot of names. We're just going to go for nonlinear. In the case of water, H2O. So this is where we've got 2 pairs of non-bonding electrons. So let's say these 2 are non-bonding, these 2 have the H on it. It's going to make this V-shaped nonlinear geometry. And then these 2 electron clouds are going to repel each other even more than these ones. And we get a bond angle. It's going to squish these closer together of 104.5 degrees. The last things we're going to look at today are some violations of the octet rule. Now, with any good rule, we have things that don't adhere to that rule. And the octet rule is one such thing that can have exceptions to it. Some compounds can be stable even when they aren't following the octet rule. We can have electron deficient ones where they don't have, or they have less electrons than 8, and hypervalent where they have more electrons than 8. And this will consequently affect the molecular geometries as well. And we can draw these out to show them and the bonding angles that they have. So let's start with the first one. Boron trifluoride has B with, boron is group 3, so we have 3 electrons. Trifluoride, we're going to have BF3, like that. Our next one is phosphorus pentafluoride. So phosphorus is in group 5, so we have 1, 2, 3, 4, 5. So we can essentially make a covalent bond with each of these. So we can have phosphorus with 5 fluorines around it, pentafluoride, like so. And then the last one is sulfur hexafluoride, SF6. So sulfur has 1, 2, 3, 4, 5, 6 electrons in its valence. So we have F1, 2, 3, 4, 5, 6. Now these will have different molecular geometries, but the idea is still the same, that these electron areas want to be as far apart as they can have. So if you're playing along, you can pause now and predict what molecular geometries these might have based on that table in the previous slide. Righto, let's have a look ourselves. If BF3 has 3 regions of negative space, we get a trigonal planar, which looks like this. This one here. So these things are all on the same plane. So the furthest these can be away from each other is just 360 degrees divided by 3, which gives us bond angles of 120 degrees. So these are all going to want to be 120 degrees away. If we have 5 things, we get this shape called trigonal bipyramidal, which is that one there. And we can look at that like so. So I've got 1, 2, 3, 4, 5 things around it. So my phosphorus, make sure I got enough room here to draw it. My phosphorus has the white balloon and the green balloon on the same plane. Is that still in there? Yep. Then we've got a red balloon over here on the same plane. Yellow balloon is coming out. That's the 5th one, that's the 4th one, and then the 5th one, the orange balloon, is going back behind. Now we can look at these in 2 different ways. If we look at the yellow, the red, and the orange, these are all on the same plane. So these are essentially a trigonal planar sitting in the middle of this, like that. Hopefully you can see that the orange, the yellow, and the red are all on the same plane in this. So that means between these ones, between the ones that are on the same plane, we're going to get 120 degrees because it's got this sort of planar shape within there. And then sitting above and beneath that, we have the white and the green, and these are just coming off at 90 degrees to each other. So I'll show you this diagram on here, which is a bit nicer. We've got the 3, 1, 2, 3. These are all sitting on the same plane to each other. So these are 120 degrees. And then above and below, coming off at 90 degrees to make a trigonal bipyramidal shape. And then the final shape is the octahedral, which is in the case of our SF6. When you've got 6 things, this is the same geometry as our p orbitals. We get this one here, where our sulfur's in the middle, 2 fluorines, 2 fluorines, 2 fluorines, SF6. And we get the bond angles of 90 degrees between any of them. So 90 degrees between all of the atoms that are bonded. 90 degrees there, 90 degrees there, 90 degrees there, 90 degrees there, so on and so forth. So we have our electron deficient to make the trigonal planar, our hypervalent compounds expanding the octet to make trigonal bipyramidal and octahedral. Then we have our tetrahedral, trigonal, pyramidal, and our nonlinear, where they've got slightly different bond angles based on the order of electron-pair repulsion. And we have our simple linear. And I believe that concludes today's lesson. We have looked at describing covalent bonding in terms of orbital overlap, giving sigma and pi bonds, including the concept of hybridization to form sp, sp2, and sp3 orbitals. We have explained the shapes of and bond angles in molecules by using the qualitative model of electron-pair repulsion, including lone pairs, using as simple examples, trigonal planar, linear, tetrahedral, pyramidal, nonlinear, octahedral, trigonal, bipyramidal, and finally we predicted the shapes of and bond angles in molecules and ions analogous to those specified in that part. Task for this week, if you are so inclined to consolidate your work, you can pause, work through those 1 column at a time from the bottom up. Thanks again, hope you join me next week when we continue our chemical bonding model. See you later.